Hello students, welcome back. We went through sampling distributions in general and the sampling distribution of sample means. Also, we discussed the central limit theorem. Now, finally, let's consider some applications. Here's an example. The intelligence quotient scores are normally distributed with a mean of about 100 and a standard deviation of approximately 16. If one person is selected at random, what is the probability that the selected person's IQ is between 90 and 105? If you're feeling the kind of deja vu, then it's not a deja vu. As a matter of fact, you're not mistaken. We went through the very same example before, back in lesson 7. As this problem, we have normal distribution around 100, and then 90 to 105, and we want this probability represented by this shaded region there. And this one is standardized version, is a standard normal, which is not really necessary. Look at this, 90 to 105, and then the center is 100. So from 90, we get a z-score. Here's the computation. N minus center over SD from this 90. And then from 105, we get the same thing. N minus center over SD. And then we get this z-score. All right, we have this z-score and that z-score. And all you have to do is going to be to look up this normal table, and then you're going to get appropriate areas. And from here, if you look up the normal table and get the area, that's going to be the area to the left, this point. Now, from here, if you get the area, if you get the probability from the normal table, from this z-score computation, because it came from this 105, it's going to be this area. And then what do I want? I want the area of the middle point, the smaller region, larger region. So we're going to subtract one from the other, and that'll give me the middle area through this computation. So that's what we did way back in lesson 7. And by the way, let's make one more observation here. Here we have sigma, but you can easily replace that as standard error and then sample size of 1, because we are looking at individual. And of course, square root of 1 is 1, so no change there. So in any case, x minus mu or SE, or n minus center of SE, that's a formula that we use all the time, even for one person. Now, for the second part, that SE is absolutely necessary. Now we are looking at 10 people at the same time. A sample of 10 people is selected at random, and what's the probability that mean IQ of the sample is between 90 and 105? You see, we took 10 people, so exceptionally smart or exceptionally dull people, those IQs will be kind of evened out because I'm taking the average there. And then considering the distribution of the average, so we expect less spread, more concentration toward the center, smaller standard deviation, or more precisely speaking, smaller standard error. Consequently, we get this kind of situation. And look at this picture. Previously, it was this picture, and looks like it became fatter. But actually, no, not really. 90 to 105, that stayed the same. It's just that this entire picture is coming like 60 to 140, but this is going from 85 to 115. So it's due to rescaling. You're getting that. In any case, you can see that this proportion is not that high. We ended up with about 35%. But looking at this picture, looks like it's going to be a lot bigger than 35%. And that's normal because we are looking at the sampling distribution of sample means. So we expect less spread and more concentration toward the mean. So more probability in the mean. All right, that's that. Let's do our computation. How do I do that? From 90, we do a z-score computation. From 105, we do another z-score computation. And here's one for 90, and here's one for 105. Shall I increase the font? This one and that one too. Here, standard error is sigma over square root of n. Previously just 16, but this time 16 over square root of n. 16 over square root of n, and that changed those numbers into this and that respectively. So from z1 we get negative 1.98 approximately, and from here I get 0.99. Look up the z-table and then find out the probability or the left-hand side shading. The detail is left to the students. If you do that right, this one corresponds to about this probability, 0.024 something. And look up the z-table for this one. From 105, I get 0.838 something, left-hand side shading. I want the middle part, so this is smaller, that's larger. Subtracting one from the other, I'm going to get the middle part. And there is a computation. Appropriate subtraction. And then what do you end up with? 0.814, 81.44%, something like that. That's this proportion here. That's the probability. Now go back to this. That's only 35 point something. The difference is individual versus the sample mean. The bigger the sample, the smaller the standard error. Consequently, we get more reliable sample. But then again, taking a huge sample means more expensive studies, so you have to balance out accordingly. But if there's no shortage of funding, then clearly it's better to use larger sample, and we saw that in an action. Let's see, enough problem for another problem, so let's go ahead and do this. The Bureau of Labor Statistics provides compensation information and services for various positions. As of May 2008, national average salary for a registered nurse was $65,130. Suppose that's the standard deviation 9,385. Find the following for the mean of random samples of 100 such nurses. Okay, sample size is 100, and then we are looking at SDSM, sampling distribution of sample mean. Sample size of 100, which means the standard error is the standard deviation over square root of 100. That's standard error. Here's a picture. So center is 65,130, and the normal picture ends in 63,500, and probability of less than that, so we have this shading. Okay, we want less than, so this shading. Now, how do you calculate our z? End minus center over SE, and 63,500. Let me expand the font. 63,500. Center, 65,130. Yeah, center is expected value. Now, what is standard error? Sigma over square root of 100. Sample size is 100. Punch it calculator, you're going to get negative 1.74, approximately speaking. And looking up the z-table, you're going to get your probability, the left-hand side shading. If you look up the z-table, then you're going to get a little bit different figure than this, because in z-table, you're using only 2 decimal digits, but here I'm using 6 decimal digits. So this one is a little bit more accurate, by the way. Okay, we got that, and A is done. How about B? The probability of the sample mean is greater than 66,000. So center is the same, 65,130, 66,000 or higher, because we want greater than. So this was a shading. And how do you get your probability? We the z-score computation, end minus center over SE. End 66,000, center 65,130, and center, end minus center over SE. Yeah, okay, let me rewrite it again. Z is end minus center over SE, and that's the formula. And end of this region, 66,000, and center, 65,130, and standard error is sigma over square root of n. And punch your calculators in, you get 0.93 approximately speaking. Look up the z table, you're going to get this probability here to the left-hand side. Subtract from 1, and you're going to get what you want. Remember, when do we subtract by 1? Whenever you have right-hand side shading, you have to subtract from 1, because if you get normal table, that gives you always a left-hand side shading. So total is always 1, so subtract from 1, then I'm going to get the right-hand side shading. How about the third problem? The probability the sample mean is between 63,500 and 66,000, like this. Well, that's easy. In part B, we did the z-score for 66,000 and calculated the area to the left-hand side. And then in part A, we did z-score for 63,500 and calculated area to the left. And subtract one from the other, you're going to get the middle area, and that's what we have right here. This minus that is this minus that, and then if you do it right, you're going to get the answer like this. And the kind of answer you're going to get with normal table is going to be a little bit different from this, because you're using only 2 decimal digits, while here I'm using 6 decimal digits or even more. A little bit more accurate number is here, but little different, and nothing is ever accurate in statistics, so it's all estimation nonetheless. Okay, that completes section 3, and we'll discuss section 4 in a separate video.